In this video, we are going to talk about databases. When you're dealing with backend systems, interacting and handling databases is one of the most important and one of the most frequent operations that you're going to perform. So understanding all the concepts surrounding it is crucial to be efficient in your job. So let's start with the question, why? Why do we need databases in the first place? Now, at its core, a database is simply a way to persist information across different sessions, to talk in a very high level. And what that means is, and persistence basically means storing data in a way so that it survives even after the program that created it has been stopped. So for example, think of your to-do list app, right? You add an entry and you can check off all the tasks that you have already finished, etc., etc. Like that's the basic functionality and expectation from a to-do app. Now, when you do some operation, when you create an item or you can check off an item and you close the app, and when you open it again, you find all the information, the state of the data that you left it, it's the same when you visit again, when you come back to the app. So that's what we mean when we say persistence. The information has to be there in the same expected state even after a considerable amount of time has passed or across different physical locations. Right? That's what we mean by persistence. If you did not have persistence, every time you open that app, you'd have to create new to-do list items and you'd lose all your progress, whatever task you had created previously, etc., etc. Right? Persistence is a very important thing and we use it in our day-to-day lives a lot. Now, what is a database? What do we mean when we say the word database? The term database is surprisingly very broad. In the simplest sense, any kind of structured storage can be considered as a database. For example, you have a smartphone and in your phone you have a contact list, right, of different people, and that list can be considered as a database. In the same way, if you are a developer, you must be familiar with the concept of local storage, which is offered by every browser. So we can check that out right now. If we open this, the developer tools, and when we go application, and we can check the local storage, and it has some entries, right? Since we are using this website called Excalibur, the website has stored some entries in the format of key value store. It also has a session storage. It also has a cookie storage, etc., etc. Like all these different types of storage mechanisms, they are also considered as a database. And even if you take a simple text file where you just jot down notes and you can refer to those notes later on, even that can be considered as a very basic database. So if we try to derive the patterns from all these examples, a database basically means is some kind of system, some kind of persistent system which offers ways to create, read, update, and delete data from it. Right? That's a very basic and high level example of database, which is not limited to what we mean when we say database in the context of backend systems. Database is a very generic term, which means a persistence layer which provides operations of CRUD, create, read, delete, and update. But when we say database in the context of backend systems, in the context of servers, right, in typical developer context, when we mention database there, what we mean is disk-based databases, disk-based, right? And by disk, I mean hard disks. It can be HDD, SSDs, or whatever modern technologies of storage we have available. But why disk storage? Why disk-based databases? Because disk storage, whether it's a traditional hard drive or a modern solid-state drive, or also known as SSD, is relatively cheap when compared to other means of storage. For example, when we consider RAM, which is also considered as a main memory or the primary memory when we take into account our CPU unit, right? If you're from a computer science background, you must have known that we have a CPU unit which can access the primary memory and It can also access the secondary memory, which we also call as disk-based memory, right? Which uses either a hard drive or a SSD. Now, RAM is very fast. It's called main memory, and it is very, very fast as compared to the disk-based alternative. But the problem is RAM-based storage. It's relatively costly, and we don't have as much supply as we do when it comes to disk based. So if you check the configuration of your system, whether it is a Windows based, Linux, Mac, does not matter. If you check the configuration of a system, most people have something like 8 GB RAM or 16 GB RAM or 32 GB RAM, or if you're on the higher end of the consumer, you must be having 64 or max to max 128 GB of RAM, right? But when it comes to hard disk, when it comes to a secondary storage, most people, since hard disks are relatively cheap these days, most people, they have storage starting from 512 GB up to 2 TB, right? That's the average storage people have in their laptops, in their systems, right? And you can see the pattern. When it comes to the storage space, we have limited amount of RAM, we have limited amount of primary memory, but we have a lot of space when it comes to disk-based memory or secondary memory. And the trade-off is RAM is very fast when it comes to data retrieval or data saving, and disk-based storage is relatively slow because of the way the data is stored and because of the way the data is fetched. And that's the reason when we use caching mechanisms, either in Redis or in memory caches, etc., etc. Whenever we talk about caching, we talk about storage in RAM or storage in primary memory, because fetching data or saving data from primary memory from our cache is very, very fast when it comes to fetching data from our databases, which are disk-based storages, also known as secondary storage. But when it comes to databases, the thing that matters most is we need more space, and we can do a fair amount of trade-off when it comes to speed. And that's the reason most databases, at least when it comes to traditional databases like relational or non-relational databases, they are based on disk-based storage or secondary storage. That's where they actually store their data. And the format they store their data, the way they store their data, all the algorithms surrounding it, etc., that's a very technically deep area, and we are not going to cover that in this video. We just want to keep this relevant for a backend engineer, right? On the application level, the only thing you need to know is caching technologies like Redis, etc., they store their data in primary memory or RAM. And databases, traditional databases like Postgres or MongoDB, which we'll cover next, all these relational or non-relational databases, they store their data in disk or secondary memory, because disk-based storages offer more capacity at less price, but at the cost of less speed. That it is clear, we are talking about databases in the context of disk-based storage, and that too in the context of backend systems. Right. Now we come to a term which is known as DBMS, also known as database management system. Now, what is a database management system? Just storing our data, whatever data we have, just storing it in some kind of disk-based storage, that is not enough. Of course, we also need different ways of retrieving that data or making changes to that data or deleting that data, right? All these different operations that has to be done, and that has to be done in a very efficient way, since we are talking about hundreds and thousands of GBs of data, right? So we need these operations, create, read, update, and delete operations, and that too in a very efficient manner. And that's the reason we have software systems called as DBMS softwares, and whose sole responsibility is to efficiently provide all these CRUD operations to the clients or to the users, whoever is using it, and storing that data. Of course, they also have a lot of other responsibilities like security and scaling their database systems and load balancing, etc., right? But on a very high level, they have two responsibilities: storing the data and providing different operations to the client or the user. Primarily CRUD operations: create, read, update, and delete. So in a way, some of the responsibilities of DBMS that we can point out is, first, data organization. They need to efficiently organize the data so that fetching, updating, and creating more data, etc., all these operations are efficient. Second, access. As I've already mentioned, they have to provide methods to do CRUD operations: create, read, update, and delete. Third, integrity. Now, it's a technical term, but what it basically means is the accuracy of the data, the validity of the data. We'll see what all these different buzzwords mean when we actually go into examples. So this just means the data is correct, right? Whatever data that we are storing, that data is valid. That data is not corrupt. So to give you a very high level example, it's an e-commerce platform and we want to store all the order details of customers, and each order will have some kind of payment information, how much was the order, etc., right? And in the database, we are storing the payment amount as a number. So it's the responsibility of our database management system or our DBMS software to maintain the integrity of the data so that no one can insert anything in that field. If we have a payment field, then for this field, we want only number data type, right? We want some kind of numerical amount. So if someone tries to store a string, something like, let's say something, and if they try to insert it here, that should fail. The DBMS software should not allow it because it's their responsibility to maintain the integrity of the data, the correctness of the data, the validity of the data, right? It has a lot of meanings in a lot of contexts, but this is what it means. The data has to be accurate. The data has to be consistent. Now, fourth is security, which basically means protecting the data from unauthorized access. Databases, DBMS softwares have different users, different roles, etc., for the sake of protecting the access to the data, right? So that's a very high level overview of what are the different responsibilities of a database management system. Now here we have a question: why do we need these DBMS softwares? Why not use just simple text files or any kind of file and store all our data in text format inside it? And when people were coming up with these concepts of databases, or before people came up with these concepts of database management system, this is how people started with. They tried to store all their data in text files, right? Now the problem with storing your data in text files is there are a couple of problems. First thing, parsing. So if we are going to store our data in a text file, every time you wanted to find a specific data point, let's say it's a customer database and you're storing all the details of your customer in your database inside that text file as plain text. And every time you wanted to find a specific customer, you'd have to write code, application code. It can be any programming language, Python, Java, JavaScript, Go, Rust. It can be any programming language. You have to write code in that programming language in your application level, in your backend code, to parse the text file, split the lines. So if we have a text file and we have different lines, you have to parse all the entries of this text file and we have to split these lines and we have to compare each field. And this whole process is very slow. If you're familiar with parsing data from our file system in different programming languages like Rust are relatively faster when it comes to parsing kind of operations, but languages like JavaScript, Python are relatively slower as compared to Rust, right? They are fast, but compared to a highly performant language like Rust, they are relatively slow. So if your programming language is something like JavaScript or Ruby, then you'll also face a huge performance hit, right? And also doing all this parsing thing is very error prone. If something goes wrong, you can corrupt your data, you can provide wrong information to your customers, etc. Like parsing itself is not an efficient solution because how slow the operation is and how error prone it is. The second thing is there is no structure. Text files do not have a formal structure. You cannot enforce that data has to be in this particular structure in this file, right? Text files are very fluid. You can store any amount of text in any format. You just have to dump it there, right? There is no structure, and that makes it very difficult to enforce consistency in data. You cannot enforce something like this particular field will only have number. You cannot enforce that rule, right? Since it is all text files, since it is all string, it will take any kind of data and it will put it there, right? It cannot promise any kind of data consistency. Third thing, concurrency. By concurrency, what we mean, what happens if two people at the same time try to update the same text file, right? Whose update is going to be considered as legit and whose update is going to get discarded? Obviously, the last one who updated this text file, only their update is going to persist. Because let's say we have a text file and we have an entry, let's say amount, right? Amount, and we have something like 40. Two people are trying to access it for the sake of modification. They want to modify this field called amount. So the first thing they will do obviously is read the file, right? They need to read the file before they make any changes. They cannot just put some arbitrary amount. They want to increase the amount. So one person wants to increase the amount by 20. Another person wants to decrease the amount by 20. Now, what happens? Both of them read the data, right? Both of them read the data at the same time. They start their operation at the same time. Okay, they both have the initial entry of 40. So the first person, they increase the amount. So they do 60. And the second person, they want to decrease the amount. So they do it 20. And they save it. Now, even though both of them started at the same time, because it was a read operation, when they save it, of course, there is going to be some kind of first comes, first serve kind of situation. You cannot tell beforehand that this update is going to persist or this update is going to persist. It all depends on what CPU cycle it is running and 1,000 different parameters, right? So depending on the environment of the system, at the end of this operation, at the end of both of these operations, the value, it might be 60 or it might be 20, right? There is no consistency here. That's what I mean by concurrency. When two different users try to do some kind of modification at the same time to the same data, you need some kind of concurrency mechanisms inside that software, inside that database software, to efficiently, to accurately manage the whole interaction, to provide a consistent result, right? And a simple text file simply cannot do that. So these are overall all the challenges that people faced. And if you try to do that today, you will also face the same challenges after some time, after your data grows, right? And because of all these challenges, because of all these limitations of simply storing your database in a text file, people came up with softwares like DBMS. And now that we are talking about DBMS, we have finally reached the stage where we can talk about different types of DBMS software. On a very high level, we have two types, the major two types. One is relational and the other is the opposite, non-relational. Relational database basically means a database system which organizes data in tables, rows, and columns. Okay, and relationships between different tables are defined using concepts like foreign key, etc. Right? Some of the key features of relational databases: data is structured and data is inserted into a database which have predefined schema. You cannot just arbitrarily insert or push any kind of data into your database. That particular data should have a particular schema, which basically means it should have a corresponding table, and that table will have a very strict schema. You have to beforehand define all the columns of a table and all the data types of those columns, right? Everything has to be pre-decided. You cannot do anything on the fly. It is a very strict system. And because of that strict schema enforcing, the advantage it offers is data integrity, which basically means at any point of time, you can bet on the state of your data. You know what is the data type of a particular column is, what are the different relationships between different tables, and a lot of different things. The data in your tables always have a consistent state. They'll always have an accurate state. Similarly, we have non-relational. Oh, right. And next, in order to interact with this database, we generally use the language SQL, also known as structured query language. In the same way, we have non-relational databases. So some examples of relational databases, which you might have already heard: MySQL, Postgres, SQL Server, etc., etc. Right? We have a lot of different relational database types. Similarly, we have non-relational. You must have heard about MongoDB, one of the most famous databases in the non-relational domain. And the difference between these is, while relational databases force you to have a consistent schema, a very expected schema, before you can put data inside your database, right? You have to have a predefined schema. But non-relational databases do not enforce anything such as that, right? You can put any kind of data, and two entries of a same table. We don't use the term table in the non-relational domain, but if you're doing a side-by-side comparison, then a table is called a collection in MongoDB, right? And inside a collection, each entry in relational, it is called rows, and in non-relational or MongoDB, it is called a document. In relational domain, each row will have the same kind of data. The structure of the rows will always be the same, right? But in non-relational domain, each document can follow a different data structure. Okay, that's the primary advantage, but sometimes disadvantage when it comes to the NoSQL domain. The advantage is obviously it has a very flexible schema. So if you're doing some kind of prototype, you want to move fast, you don't want to spend time figuring out your database schema, enforcing the schema, maintaining it, etc., etc., then you can go with something like MongoDB and move very fast without thinking about your database schema. You can push data on the fly, you can fetch any kind of data, etc., etc., right? The flexibility can be an advantage in some scenarios. So if you want to take an example, let's say we have a CRM, also known as customer relationship management software. And inside this, what usually happens is it needs to maintain accurate and consistent data about customers, data like contacts and all the sales opportunity details, etc., etc., right? And this data, this critical data, is more suited to be inside a relational system. A relational database like Postgres is a very good choice because it provides strong data integrity and allows for complex queries and analyze relationships between customers. So a CRM system is a very good candidate when you are trying to decide between a relational database and a non-relational database. In the same way, if we want to find a use case for a non-relational database, we can take an example like CMS, also known as content management system. So content management systems are used to push content from a remote site to different content distribution system. For example, let's say you have a blogging platform. So every time you want to add a new article to your website, you don't want to open your code base and write a new file and push it to GitHub and deploy it, etc., etc., right? You can pull that data in your website dynamically from a content management system. It can be something like Sanity, etc., etc. Like we have a lot of CMSs in the market. So you can pull that data from a content management system and you can render that data. So every time you want to add a new article, you just have to log into your CMS system and write that blog or article in the markdown format and save it. And the next time someone refreshes your website, the new article will be fetched. So when you have a use case like this, the content that a CMS needs to store, that is not really structured. So an article can have an image, it can have a code block, it can have a YouTube embedding, etc., etc. Like content can be of a lot of types. So a non-relational database, something like the MongoDB, makes a lot of sense when you don't know beforehand what are all the different types of data that are going to be stored here. You just want to take everything and dump it here, right? So in these use cases, MongoDB makes a lot of sense. But even though databases like MongoDB, they offer a lot of flexibility, they can also present challenges in terms of data integrity, which is a very important concept when it comes to database systems. And because they often lack the strong constraints and relationships of relational databases, it's easier to introduce inconsistencies into the data. Since the schema of the data, the integrity of the data is not enforced at the database level, you have to do it at the application level, which adds more complexity to your code. And of course, it is more error prone. Since application code is generally changed a lot, and it's very easy to miss something, right? To introduce new bugs to your code base. So now we have to make a choice, right? We are going to learn about databases, and there are a lot of options in the market. We have relational, we have non-relational. Inside relational, we have MySQL, we have Postgres, we have SQLite and SQL Server, a lot of different products, and all of them pretty much offer the same kind of features, and all of them can scale when it comes to implementing in your production systems. So we have to make a choice here. What database are we going to proceed with? And when you have a situation like this, going with Postgres makes a lot of sense. Why? A couple of reasons. One, it is open source and free, right? It is not a proprietary software. It is completely open source. You can go and look at the source code of the Postgres, even though you won't necessarily be doing that. But still, it is an open source software, and a lot of companies prefer open source softwares so that they can host it, they can deploy it in their own premises, in their own servers, etc., etc., right? Second, the Postgres DBMS system, it sticks to the SQL standard. So you can take any SQL query and you can run it on a Postgres system, and it will perform the same way it performs in a different database system like MySQL or SQL Server, because the Postgres database system sticks to the SQL standard. So in the future, if you want to migrate your database to a different system, then you won't have to do a lot of work. Let's say you want to migrate to MySQL for some reason, right? So since Postgres is SQL compliant and you have written all your migration statements, all your create, update statements and fetch statements in standard SQL format, then you can just change your database and do some minor changes, and you can easily switch from Postgres to MySQL, right? That's one of the other reasons to go with Postgres. It is very easy to migrate to a different system if you need it. 3, it is very extensible, which means it offers a lot of features. If you go to the Postgres documentation, it is around 1400 pages long, and it offers a lot of features, pretty much covers every single use case a typical SaaS might encounter, right? And it also has a very good extension based system, so you can customize it depending on your own needs. Fourth, it is known for its reliability and scalability. And fifth, I think this is the one thing that makes it easy to make the decision. It has very good JSON support. Now, as we discussed just before this, that one of the primary reasons to go with something like MongoDB, a non-relational database, is you can take any kind of data. So when we say any kind of data, we mostly mean JSON, any kind of JSON, because in JSON you can pretty much store any kind of data, right? It can be number, it can be string, other JSONs that are embedded inside it, arrays, etc., right? So you can store any kind of JSON as a document in a NoSQL database, in a MongoDB database. In the same way, since Postgres offers a JSON data type and it has very good indexing and query capabilities for JSON fields, there is no other reason to go for a different database just for dynamic data, right? You can use Postgres with JSON fields for your needs of dynamic data, as we saw in the previous examples of a content management system. If you have some kind of content that you're getting from the user and you want to save it in your database, and you don't have a strict schema for that content, you can go with a typical JSON schema and dump whatever content that is coming from the user there. And when you want to render it, you can fetch it from there and you render it, right? There is no need to switch to a non-relational database just for the needs of your dynamic data, right? And because of all these features, Postgres is pretty much the number one choice when it comes to, at least what I have seen, a lot of startups and a lot of big companies also stick with Postgres, and Postgres is usually their first choice. And even though if you do your own research, you will find a lot of articles where you will see MySQL has a lot of performance benefits, etc., etc. Right? But until you are serving millions of users and you want to optimize a very specific bottleneck of your application, you don't really need to think about whether you should go with MySQL or whether you should go with Postgres, right? Since the rich set of features and the very good JSON support of Postgres should be your first choice in pretty much all your projects. And that's the reason in this video, we are going to go with Postgres. Whatever all we are going to learn about databases, we will learn in the context of Postgres. And with that, I want to give a note here that there are already thousands of free resources available on YouTube, elsewhere like Udemy. You have paid resources and you have hundreds of free resources that cover the basics of SQL and PostgreSQL, right? SQL is, when we say SQL, it is the language that you use to query, and Postgres is the database system, the software on which we execute our SQL queries, right? So there are a lot of courses, free courses available right in YouTube for both SQL and Postgres, right? So instead of repeating the same thing, instead of doing all the create table, select, the basics of order by, group by, right? All the basics of SQL and the basics of Postgres again. In this video, we are going to save some time and we are only going to stick with some concepts that are very relevant when it comes to backend systems. And we are going to leave the basics so that you can learn it elsewhere. So if you want, you can pause this video right now and just search in YouTube SQL basics. You will get videos from 1 hour to 20 hours, and same for Postgres basics. So you can choose a video according to your own comfort, what amount of comprehensiveness that you need. You can watch a video of 1 hour and come back to this video, or you can spend a couple of days learning about SQL basics and Postgres basics and come back to this video, right? So that is one of the prerequisite before you proceed to the next section. So we're going to skip all the basics so that you can do your own research. This is Table Plus. It is a graphical software for interacting with your databases, and it has a very modern UI feel. And this is the software that I use on my day-to-day basis for all my database query operations and exploring, etc., etc., right? So we'll be using this in this entire video to go through different demos and to explore different concepts. Now, starting with, what are all the different data types that we have available in Postgres? I just want to bring this, even though just before this I mentioned that we won't be covering the basics of Postgres and basics of SQL in this video, but I feel this is an important piece of information that we have to cover before we proceed, so that we don't have to repeat this again when we are actually talking about our backend system, right? Now, we won't be going very deep into each data type. We'll just do a very high level introduction. This is a create table query. If you're already familiar with the SQL language, then you'll recognize this. This is how we create a table in any relational database, whether it is Postgres, MySQL, etc., etc., right? Now, we are creating a table whose name is data types demo. And these are all the fields, which basically means these are all the columns that are going to be in this table for each row, right? So starting with, we have serial. What does serial mean? It is just an integer data type, but each time we add a new entry into the table, this will increment the value. So by default, let's say it starts with 0, right? The next time you insert a row, and if you omit this ID field in your insert statement, value of this column for that row is going to be 1. Same way, the next time you enter something, it will be 2, 3, 4, etc., right? And usually we use serial or big serial. So there is another version which basically has more capacity. The maximum number that you can store in big serial is a lot higher when it comes to serial. So usually when you're dealing with production systems, we go with big serial when we want to make ID as our primary key. So primary key is basically a unique field using which we can identify a particular row in a table, right? Now, serial is an integer which is going to be automatically incrementing with each entry in our table. Then we have small int, we have big int, and we have integer. All these three are basically integers, just that the capacity, as I said, the maximum number that you can store in integer. So this is how the scale works. We have integer, which is less than small int, which is less than big int. So depending on your need, you can either go with integer, small int, or big int. Same way we have decimal and numeric, which are mostly considered identical. You can use either of them. They pretty much behave the same way, right? And the purpose of this is, what does this 10 and this 2 means is, it basically says you can store a number. You can store a number in this format, right? On the right side of the decimal point, there will always be two numbers, right? That's what this 2 means. On the right side of the decimal point, there will always be two numbers. And what this 10 means is, across all these numbers in this complete number, across all these numbers in this numerical representation, the maximum amount you can store is 10. So you can store something like 1, 2, 3, 4, 5, 6, 7, 8 dot 90, right? Now, if you count it, we have 10 numbers. We cannot store something like 3 here. We cannot add something like this because the maximum we can store is 10 numbers across this whole numerical representation, right? And on the right side, we have two numbers. This is what this means. And the question mostly people ask is, what is the difference between decimal or numeric, something like this, as compared to something like real or double precision or float, right? Now, the difference is a little complicated. Floating point numbers, they can be real, double, float, whatever you call them. They are represented in a very different manner as compared to the decimal counterparts, which we have in decimal and numeric. So the thumb rule that you should have is, if accuracy is an important aspect for that field. So let's say you are storing an information like price. For a field like price, accuracy is very important, right? Because it is going to be involved in a lot of calculations, and a lot of things can go wrong if you have different representations of the same number in different systems, etc., right? The accuracy is very important when it comes to a field like price. So in this case, you should always go with decimal, right? You should always stick with either decimal or numeric, but standard says you can go with decimal, right? So if accuracy is an important aspect, then always go with decimal, because floating point representations can have different values across different systems because of the way they are stored, because of the way they are processed. They have a very different algorithm when it comes to rendering. Or at the same time, let's say you have a field like size, right? And it is a size of a area, right? It can be something like 567.8987, something like this, right? Some fractional number, some floating point number, where accuracy, let's say if 8987 turns into 900 or 8967, something like this, right? Very small discrepancies in the accuracy or the representation of the number does not impact a lot of difference in your systems. When you have numbers like this, you should go with floating points, right? Now, if you have a question like, if decimals are always accurate, then why shouldn't we always go with decimals? And the reason is because decimals always have accurate representation of their value, and because floating points don't have that kind of accuracy, floating points are considered faster when it comes to such storage, when it comes to performing different calculations, etc., right? Floating points are very fast. That is the reason in a lot of scientific computation based domains, floating points are preferred as compared to decimals or decimal representations. So you should always evaluate what kind of value that you're going to store. And if it is not something that is going to have a lot of impact, if there are small discrepancies in the representation of the number, then you should go with float because they are very fast to process and very preferable in these kinds of scenarios. But if it is a value like price or something very critical where accuracy matters a lot, then always go with decimals, right? That covers pretty much all the floating point data types. Then we have a very interesting category, which are string categories. And we have 3 types in that. We have char, varchar, and text. Now, all these 3 data types store text. That is the similarity between the 3 data types. The difference is when we say char 10 and inside this field, if we say store something like AB, if you store something like this inside a data type, which is declared as this, and the length is defined as 10, then what the database system will do is it will pad extra 8 spaces in that field before saving, because we have defined the length as 10 and it is a char data type, right? That is the property of character data type. Whatever length that you have defined, does not matter the actual value that you are trying to insert, it will always try to store the same length. If you don't provide the same length, then it will just pad some empty spaces, right? Inside whatever way it is represented, it will add some empty spaces, and that's how it will store it. And that is the reason people came up with another standard, which is called varchar, also known as variable character. Now, the way it works is when we say the length is 255, what it means, 255 is the maximum length that you can store in this field. But if you store something like this, AB, then the length will be 2, right? It won't add extra spaces just to make up for this 255 length. If you store a smaller value, then it will be 2. If you store something like A, B, C, D, then it will be 4, etc., right? Depending on what values are actually being inserted into the database, it will adjust itself. Just that the maximum amount, the maximum number that you can store is 255. You cannot exceed that. If you do, then you will get a database level error. Now, the last thing is text, which is a very modern alternative to varchar. So imagine varchar without any length field. Basically, any amount of text, a text of any length. That's what text means. You don't enforce any length on this field. You can store a text of any length. Usually, it has some kind of upper limit like 250 MB or something. You can do your own research for that. But yeah. And when we say 250 MB of text, it is a very, very, very long text, right? Usually we won't be needing that much, but that's what it means. Now the question is, when you want to store a string, which one you should go with? The first thing is never choose char, right? It is a very old standard. People used to do it way back. So either go with varchar or text. You can use char if you know beforehand that the length is always going to be the same, right? It cannot be variable. So let's say you are storing the codes of all the days of a week. So the values can be MO or TU or WE, etc. You get my point, right? If you have a requirement where you know that you have all these values and all of them have the same length, then you can go with a data type like char2, and this way you won't be wasting a lot of space because of the variable length of different entries of the data, right? Only go with char if you have a use case like this. But if it is a general text, let's say name of a customer, name of a product, etc., or a description, etc., then either go with varchar or text. Now, how do you choose varchar versus text? What I believe personally is you should always go with text, because if you go explore the documentation of Postgres, they themselves recommend that always use text, which is the model alternative of varchar without length. Because most people, what they confuse with is, if you use varchar with 255, this is going to perform better as compared to a field like text, or you cannot index a field. We'll cover index shortly, but people believe you cannot index a field of type text. There are a lot of misconceptions around this because other databases like MySQL, SQL Server, SQLite, they have different conventions. The way they operate, the way they function are very different from Postgres. And when people switch between different databases, they get confused or they are misguided. So if you explore the official documentation of Postgres, they recommend that always go with text. There is pretty much no performance difference between varchar or text. And the second thing, which is my personal opinion, that using something like varchar 255, which is, by the way, a convention from MySQL, that people from MySQL, which was a very popular database, and that has a convention of using varchar 255. And that's the reason a lot of people still use this. And 255 is, at least when it comes to Postgres, 255 has a meaning in the context of a MySQL database. But when it comes to Postgres, people just use the number 255 as a random number, right? It has no meaning whatsoever in a Postgres database. And people just use it without thinking, just because the way it has always been done. And that's why I personally believe, instead of going with a random number like 255, go with text. And the reason is, let's say later on you want to increase the length for some use case. Let's say you are dealing with a field called description, and you just set the length is 255 as varchar. So later on you want to increase the length. So to cater to that requirement, you have to do a database level migration, which affects a lot of data and a lot riskier. Of course, migrations are performed on a day-to-day basis, but still you should always avoid a database level migration if you can, right? And that's the reason using something like text and enforcing the length or whatever it is on your application level. And since we are not in the data engineering domain, we are not in the data analyst domain, people in those domains, they usually deal with SQL directly, right? They have some kind of interface and they write SQL directly and they see the result of the SQL data directly, etc., right? SQL is their first point of interaction. But as backend engineers, when we are dealing with backend systems, we usually interact with SQL databases through a driver, right? We have different drivers depending on what programming language that you are talking about. And that's how we interact with the database, through a driver. And we have a lot of application code when we are dealing with the data. That's the reason we can enforce the length or whatever constraint it is on the application code, so that our database migrations, all the database statements are simpler to read and simpler to maintain. So let's say someone new comes over and they look at this, they see varchar 255 and they think that this has some meaning, even though the person who just created it, they just added it without thinking, right? It is just a random number for them. But if someone new comes over, they will think there is some meaning to this number, or there is some meaning to this 10 number. They'll try to understand where this is coming from. And since there is no documentation, they'll try to go dig through the code, etc., etc. Like, there's a lot of headache that comes with it, because a number like this, a number like this represents that it has some kind of meaning, even though it doesn't most of the times, right? So instead of this, if you go with just text, then it is a lot simpler to read, a lot simpler to write these migration statements, all these SQL statements, because you won't have to think about these lengths and all. And if someone new comes over and they read it, they just think that it is a text field, it is a character field, right? There is no extra meaning to this. So those are some of the concepts surrounding string fields, string data types in Postgres. Moving on, we have Boolean. We can store true or false In this field, we have date. We can just store the date in this, and we have time, where we can store the time, right, in hour, minute, seconds format. Then we have timestamp for storing the information of date and time at the same time. Then we have timestamps with this extra Z at the end, which just means store the time zone information also in this. So it will store timestamp and a time zone information. Then we have interval for storing like 10 days or 1 week, etc., like those kinds of data. Then we have UUID. UUID is a very popular choice when it comes to making table primary keys, right? Because of their URL friendliness and their unique nature. So that's the reason Postgres offers a native UUID type right inside the database. Then we have JSON and JSONB. As I mentioned before, Postgres offers native JSON, and we have an extra type which is called JSONB, also known as JSON binary. And the primary difference between JSON and JSONB is when we use a field called JSON, this will be stored as a plain text with the key value format that we usually see when we are reading JSON. But when we use this JSONB, this will be converted into a different format. Postgres will serialize it into its own native JSON format for efficiency purpose, so that it can perform better. It can perform a lot of query capabilities, etc., right? It is something that is limited to Postgres. It is not an SQL standard, and most of the times you should go with JSONB because of the performance advantage that it offers. Then we have the array types. You can store an array of different data types, right? You can store an array of integer, you can store an array of JSON, date, time, etc., whatever, all the different data types that we have. Then we have some other random data types like storing network addresses, MAC addresses, and geometrical points, XML, etc., that we don't really use on our day-to-day basis. But if you do want to use it, you can explore the official documentation and you'll find more information on that. And this is how we insert data into our database. We write insert into the table name and the order of all the fields that we want to insert the data in. And then we provide all the values in the same order that we wrote our fields in, right? And this is how we are inserting all the data. This is an example of small integer. This is an integer, big integer. As you can see, it is a lot higher than a normal integer. Then we have decimal, we have real, double precision, which is basically floating point representations. Then we have character, varchar, and text. Then we have boolean. We can either pass true or false here. We have date, we have time, an hour, minute, seconds format. We have timestamp, where we have the date and the time. We have timestamps, where you have date, time, and the time zone information. Then we have interval. We have UUID. This is what a typical UUID looks like. We have JSON, JSONB. And while inserting, even though JSON and JSONB looks the same, but Postgres serializes JSONB into a different format for faster processing and faster retrieval, right? Then we have array. Then we have IP addresses, MAC addresses, geometrical points, and XML, etc., right? All the data types that we basically saw. And that's pretty much all about all the data types that we are going to deal with as backend engineers in a typical database system. Next up, what we are going to do is we are going to design the database of a project management platform. In the previous video, we created the APIs. We modeled the APIs of a project management platform. Similarly, to understand different concepts of databases and different relevant concepts, not just theoretical concepts or very advanced concepts that we don't necessarily use on a day-to-day basis, but very relevant concepts in database systems, especially in Postgres, we are going to design a database of a project management platform. And we are also going to write queries for different APIs using the same databases. Now, before we get into that, I just want to bring up one topic, which are known as migrations. In backend systems, especially in production systems, you don't necessarily just open a software like Table Plus and you just start writing queries, right? You cannot do that, because if something goes wrong, or even if something does not go wrong, but there is no way to track what all changes that are applied to a particular database over time or who applied it, right? There is no way to control the version or the control the state of the databases across different times, right? And that is the reason most database systems follow something called as database migrations. Now, database migrations are basically different files. Let's say we have one.sql, you have a folder which are called migrations inside the folder database, right? You have a folder structure like this. You have DB folder, inside that you have migrations, and inside that you have different files. You have one.sql, you have two.sql, you have three.sql, etc., right? And in each file you have a couple of SQL statements, normal SQL statements, nothing fancy, right? You have create table or create index or drop table, etc. And with that you have a tool. Usually it's a command line tool. We have a lot of command line tools for performing migrations and maintaining migrations. For example, we have dbmate or we have go migrate, right? A lot of these famous tools. Now what this tool does, it goes to this location db migrations and goes through all these files in this sequential manner, and because of that we write the names of these files in a sequential manner. Either we perform some kind of numerical series 1 2 3, or we add dates or timestamps. And since timestamps follow a single flow, that's the reason we get sequential files, right? Okay, now what this tool does, it goes through all those files in that sequence and applies all the SQL statements, basically executes all these SQL queries on that particular databases. Whatever database that you have configured in your environment, it executes all these SQL statements on that database. Inside migration also, we have two kinds of migration. We have up migrations and we have down migrations. Now, some of the modern approaches of handling databases, they don't really believe they don't really implement down migrations, but this is the standard way of operating, right? You have up migrations. Up migrations are basically whatever change that you want to do. You want to create a new table, so you write create table, etc. You want to create a new type. Let's say you want to create a new enum type, so you write create type enum, etc. Then you want to create some indexes, whatever. All the create statements you write one by one, right? With proper SQL syntax or Postgres syntax. Then, depending on the tool, let's say a tool like dbmate, what it does, it divides the same file, the same SQL file, let's say one.sql, into two sections. One section with a comment for up migrations and another section for down migrations. Now, the purpose of down migration is whatever change you did in your up migrations, whatever change you applied to the database, in the down migration, you have to revert all those changes. So that the reason for having this feature called down migration is, let's say you applied some migrations, you applied some changes to your database systems, and something goes wrong, right? Or something breaks in your production system, or anything can go wrong. What you want to do, you want to roll back to previous version of the database without any changes, right? The state has to be the same. For that to happen, you have to have down migrations, so that all the changes that you did in your up migration, the down migrations can revert that, so that you can go to a previous state. You can roll back. Okay, that's how a migration workflow works. You have a tool, and that tool usually creates a table called schema, something like that, in your database, and using which it tracks that which is the current version of the database, right? Let's say you have 1.sql, 2.sql, 3.sql, right? Then in your schema table, you will have something like 4, right? Current schema is 4 because 4 is the latest changes that you have applied on your database. When you come back and you want to add another file, 5.sql, before you apply that file, before you up that migration, your current database schema will still have 4, right? That's how the tool works. You have a migration tool which goes through all your SQL files, applies all the SQL queries on your databases one by one. If it is an up migration, then it applies all the changes. If it is a down migration, it reverts all those changes for that version. Now, the question is, why do we need migrations? There are a couple of reasons. One reason, as I've already mentioned, you cannot just open a graphical tool and execute SQL statements, because that's very hard to keep track of what are all the changes that you made, right? Unless you want to save it to a particular file and you want to commit to Git, etc., etc. And after all those things, you'll come up with your own migration system. That's why we have this concept called migrations. Couple of advantages of using migration is, one, as I said, keeping track of database changes, over time, right? You have a file, you have a lot of files in a particular folder, which is committed to your version control system. Let's say it's Git or GitLab, Bitbucket, whatever platform that you follow to version control your code. Usually your migration statements stay with your code and you commit it to GitHub, whatever platform you follow. And over the time, you keep adding new migration files to the same folder. And that's how you keep track of all the changes that are happening to your database schema. Second is rollback. As I already mentioned, if something goes wrong, you can roll back to a particular version. So that's pretty much all there is to it. Migrations are a system using which you apply new changes on top of your databases. You can add new tables, you can modify tables, you can create indexes, you can create triggers, etc., etc., right? Whatever change that you want to perform on a database, you have to create a new migration for it, because relational databases follow a particular strict schema. You cannot just insert data randomly into the databases. You have to follow a particular schema. That's the reason we have these migration statements, to make changes to the database over time using any command line tool. Now we will start modeling our database for our project management platform. And for that, we'll write migrations. Okay, here I have my VS Code open. This is where we'll write all our SQL statements to model our database, right? So for the sake of migration, we are going to use dbmate. It's a command line migration tool that helps applying all the changes to your database, right? And for that, we have to provide the URL of our database to the tool. And for that, we have to create a new environment file, .env. And inside that, we can create a variable called database URL, and the tool will pick up the value of our Postgres database URL from this location. Okay, so to create our first migration, dbmate offers a command. We can write dbmate new create users table. Okay, that sounds right. So we press enter. It creates a new folder called db. Inside that, another folder called migrations, and inside that, a migration file. So as I said, it can follow a sequential number like 1, 2, 3, 4, 5, or timestamps, whichever sequence that you want to prefer, right? In this case, it's adding a timestamp, then the name of our file, which is create users table. For now, it's empty. We'll add our migration statements here pretty soon. So this is how, as I mentioned, this section is for writing out down migrations. Whatever SQL statements that we write after this comment are considered as down migrations, and whatever SQL statements that we write before this down migration and after this up migration are considered as our up migrations, right? Now, to save some time, I'll just paste all the SQL statements and then we can go through that one by one. Great. I've pasted all the SQL queries that are needed to perform this migration, the up migrations, and create all the necessary tables. So let's explore all these statements one by one to understand all the concepts surrounding it. The first thing that you notice is we are creating some data types called as enums, right? Now, enums are basically all those values for which you have a predefined set of allowed values. For example, we have a field called status in the projects table. And for that, we only want to allow these three values. The project status can either be active or completed or achieved, active or completed or archived, right? In the same way, for tasks in the task table, the task status either can be pending, in progress, completed, or cancelled. Same way for members, they either can have the role owner, admin, or member. The reason for using a data type called enum instead of just going with our standard text, because First thing, data integrity. Data integrity, when we say in the context of databases, we mean we leave the responsibility of checking the validity, checking the accuracy of the data to the database instead of our application code. Because we created types, these enums types, and we used these types. Let's say we created this type called project status, and as you can see, we used it here, right, in the status field. That's the type of the status field is our custom enum type, which is project status. Because we did this, whenever we insert data or whenever we are trying to update data in the projects table and in the field of status, if we try to insert any random string, or let's say we try to insert, we have active, completed, or archived, we try to insert something. If we try to insert some random string like this, we will get a database level error. We don't have to check this in our application code. We can leave that responsibility for the database. We can check it in our application code. That is just decreasing the scope of the error. But still, to make it more robust, to make it more secure, we can provide a set of allowed values and we can use that custom type for any field. Then whenever we insert some data, whenever we update some data, the database will check whether that data, whatever value that we are providing for the project's status, whether it is one of these. If it's not, then we'll get a database level error. Okay, the first thing is data integrity. The second thing is documentation. And I think this part, the second point, is more important than the first point, because the first point, data integrity, this we can do in our application code, right? Since we are talking in the context of backends, we have a programming language in our hand and we can validate whether whatever status that is coming from the user, that is coming from the front end, or whatever application code, whether it is one of these strings or not, active, completed, or archived. We can do that in our application code. But another advantage of using enums in our migration statements is when you're going through your old migration statements for debugging something, or let's say you are onboarding a new team member into your team and they are going through the database migration statements to understand what all changes that the project went through over the last couple of months or the last couple of years. And they want to understand, right, what is the state of the database, what are the past states of the database, what changes happened over the time, etc., right? And when they are doing that, when they are going through all the database migration statements, if they come across this table called projects and they see the field status, and if it is of type text, but in our application code, we are only doing active, completed, archived. Now there is no way for them to find out this piece of information, that you cannot put any arbitrary text in your status field. It has to be either of these three, right? So to find out that piece of information, they have to go through all the application code. They have to see what are all the places where this field is used, and to track down all those use cases, then they can boil it down to these three values, which is a lot of headache, right? So using enum type provides some kind of documentation for you, for your team members, for your future team members, so that at one glance you can tell what are all the allowed fields that can be in a particular field, which makes everything very easy to understand, right? So that's all about enum fields. We are creating 3 enum types, and this is a syntax. We write create type, the name of the enum, and we write as enum, and inside the braces we provide all the allowed values. We create 3 types, 3 enum types, and we are going to use this in our future tables. Now moving on, we are creating a users table. Since it's a project management platform, of course we'll have users, right? So that's the first table we are starting with. We are creating a table called users. And if you notice this, each table has some default fields. We have ID, we have created it, we have updated it. Same for user profiles, we have ID, created it, updated it. For projects, we have ID, created it, updated it. So each table has this kind of metadata kind of field. The ID is not really a metadata, it is the primary key. And by primary key, I mean using this ID, we can uniquely identify a particular row in this table, right? Let's say we want to find out, or let's say in our backend API, we have a requirement that we want the information of user. Okay, since it's a UUID, let's generate a random UUID and let's paste it as a comment here. Okay, now we have a requirement in our backend. We have a API which takes the user ID in a dynamic parameter, and we have to return the details of that user. So this is the ID of that user, and we have to find out the information of the user using this ID. Now, if we don't make a particular field, let's say the ID field primary key, okay, we don't assign the condition primary key to a particular field, there are a couple of things that can happen. This primary key property has some implicit properties. Those properties are, if you write primary key for a particular field, that field cannot be null, not null. And it also has a unique constraint. So relational databases have this concept called constraints, right? You can apply a particular condition, particular property to a field, and that property or that condition will protect that field from going corrupt. Okay, that's a very high level definition. We'll see what that means when we encounter more examples. So when we say primary key, it means it implicitly has these two properties, not null and unique. So this field cannot be null, and this will always be unique. If there is another entry with the same value gets inserted into this table, we'll get a database level errors. And because of these implicit properties and some other foreign key behavior, we use this property called primary key for our ID field. So each table will have a field by convention called ID, and we will assign the property primary key to that, which will help us fetch different information of the user. Okay, now what we are saying, we have a field called ID. It is of type UUID, and it will be a primary key for this table. And by default, if the ID is not provided when an insert statement is executed, by default generate a random UUID. Okay, this is what this means. This is by default natively provided by Postgres. So if we don't provide the ID field, which we generally don't, we leave it to Postgres, the database system, to generate a random ID for us and to assign it to that row. Next, we have another field called email, and it is of type text. It is not null. One thing to keep in mind is, by default, all the fields in a Postgres table can have null values unless you explicitly specify that it cannot have null values. More than 70% of your table's fields should have the not null constraint, right? Because this not null constraint enables the database to have a consistent state. If you don't add this, then the application can push null values into the table, even though you don't do it intentionally, because a lot of database interactions are also dealt with automated scripts. So that script can have a bug and you'll end up with a lot of null values in your database, which makes things very, very difficult, right? So for a lot of reasons like that, always try to stick to not null, okay? Unless you have a reason for that field to be null. Okay, that's the reason we are writing not null here. We have a field called email. It is of type text and it cannot be null. And we have a constraint called unique. What this means is each row of this table will have a unique email. The moment you try to push another row with the same email address that already exists in the table, we will get a database level error that it violates the unique constraint. Okay, and since email is something that we don't want to create two users with the same email, we are applying this constraint called unique. Next, we have a field called full name. It is of type text, again not null. Then we have password hash. It is again of type text and not null. Since we don't directly store the plain text value of the password, we hash the password and store it. So it's called password hash, just a name. Then we have two other fields, created at and updated at. And the reason is we want to know when this user was created. Okay, when was the first time this user was created in our database? That's the reason we maintain this field called created at. And usually you don't manually insert it. We are providing this default property, And we are saying if created at is not passed by default, you can take the current timestamp and you can put it in that row. Okay, and it is of type timestamp with time zone. Okay, this is of type timestamp with time zone. This will have the date, the time, and the time zone information. Same way, updated it. We create this field so that we can keep track of when was the last time we updated some field of this row. Okay, and that can have some use cases. For example, if you have a table in your front end and you want to display all the users in the order of when was the last time their name was updated, something like this, right? So in that case, you can use this updated at property to sort by, and that's all about users table. Some of the other things to notice here is all our tables have this plural form, right? We have users, we have user profiles, projects, and that is a standard. A lot of people also prefer the singular form, user profile, project, etc., etc. It's a matter of what your team has decided and what your company has decided, but the industry standard is to mostly stick with the plural form. Second thing, all the table names and all the field names will be small case and snake case. And by that I mean, if it is a single word, it will have small case, of course, as we have users, ID, email, right? All small case. If it has multiple words, let's say full name, password hash, created at, updated it, then we'll use snake case. If you are coming from other programming languages or etc., you might have the instinct to go with camel case, right? You might want to write something like full name with N capital, and you want to merge and get rid of the snake case, but that is not a good idea because in Postgres, everything is case insensitive by nature. So even if you write camel case, Postgres will take it as. So if you write something like this, full name, Postgres will understand this full name, unless you write it like this, full name with quotes. And when you're writing your application code, using double quotes again and again can be very difficult and make the code very ugly. That's the reason we always try to stick with small case. We make everything small case, and if you have multiple words, we stick with snake case so that we can avoid using double quotes to make Postgres understand case sensitivity. Okay, that's some of the things that you have to remember. Moving on, we have another table called user profiles. Now, if you check the comment, it says one-to-one relationship with users. Now, you might have a question like, why are we creating a different table for storing information of the user, right? Why don't we store all this information in the same table? And the reason for that is when you're designing your database, you have to take into account some of the different situations that you might modify your data in. So if you think about a user, the only times you are going to make changes to a user's entry in the user's table is when they are modifying their profile. And their profile can have a lot of other information. For the sake of this example, we have just limited it to their image URL, their bio, their phone number. But a user can have other fields also, right? They can have their social media accounts, and they can have their websites and their projects, etc., etc. A lot of different information a user profile can have. And because of that, in the future, we have to make a lot of migrations to the user table itself, and we have to constantly modify the user's row again and again. And we don't necessarily have to do that if we abstract out the user's profile information into a different table, which can scale over time, which can get bigger over time, and which does not affect the primary user's table directly. These are some of the use cases that we go with one-to-one relationship for storing users' profile information, for storing user preference, for storing metadata, etc., etc. Right? This is a common convention that you will see when it comes to modeling your database. So we have a table called user profiles. Inside this, we'll store the information of the user. For this, what we can do is we don't necessarily have to create another ID field, because this is a one-to-one relationship with another table. Each entry of that table or each row of that table will only have one row in this table. That's why it's called one-to-one relationship. And because of that, we can get rid of this ID and we can make the user ID, which is the foreign key in this table, as the primary key. So we can write UUID, then instead of not null, we can write primary key, and we can also get rid of this unique thing. Now, this user ID field is both the primary key and the foreign key in this table. And we have some other fields for storing the image URL, the bio, the phone number. And if you notice, we are not writing not null here because these can be optional fields. A user can choose not to have a bio, they can choose not to provide the phone number or to have a image, customized image, etc., right? That's the reason we are not writing not null in these fields. Okay, moving on, we then have another table called projects. Now the same thing happens here. We have a primary key with ID and we are generating a default random ID each time we enter a new project into the database. Same way, we have the name of the project, which is not null, and we have the description of the project, which can be null. We don't care much about the description, but we have to have the name of the project. That's why we are writing not null here. Same way, we have a status field, which is using our custom enum type, which is project status, which is not null. And if you don't provide any value for this field, by default, it will be in the active state. Okay, usually when we are going with enum types, we provide a default value with 1 entries of that enum to make things easier for us, so that we don't have to explicitly push that value from our application code. Then we have an owner ID, which is a foreign key, and we write it like this. It is a not nullable field and it says it references the user's table, and this is a constraint that on delete restrict. And this is what it means. This owner ID is the foreign key for this table and it references the user's table. And usually this is how we write user's ID. And because the ID field is the primary key in the user's table, we can omit this part and we can only say references users, like we are doing here. And it means owner ID references the ID field in the users table. Okay. Now the second part, we are putting a condition here saying that on delete restrict. This is also known as referential integrity, which basically means that we can protect the data across different tables using the relationship between those tables. In this case, what we are saying, if someone deletes this particular user, which user? The user whose ID is in this table, the projects table, as the owner ID. So let's say we have a users table and we have projects table. In ID field, we have, for the sake of this example, let's say we have ID is 1. And in projects field, we have another entry, owner ID. In this row, owner ID is 1. So this user has created a project. That's why in the projects table, we have a row which has a field called owner ID and the value is 1. When we write on delete restrict, what it means is if someone tries to delete this user whose ID is 1, the database system will check whether this user has some corresponding rows in projects field. Since it has, what it will do is it will check what is the referential integrity constraint. What is the condition we are mentioning here? Since we are saying restrict, it will fail that operation. You cannot delete a user unless you delete the project first. That's what it means. Using referential integrity, we can put some restrictions on some operations on some tables using the relationship between those tables. And inside referential integrity, we have a couple of constraints. One is on delete restrict. Second is on delete cascade. And what on delete cascade means, let's say if we had, instead of on delete restrict, we had on delete cascade. So when someone deletes a particular user, the database system will check if there are entries in the projects table which has owner ID as 1. It will also delete those projects. Instead of restricting, it will cascade, which means it will delete the user and all the associated projects from the projects table. They also have another condition called set null and set default, which basically means if someone deletes a particular user, then owner ID in case of set null will be set null. But since we are saying not null here, and if we try to set null, then we'll get a database level error and this operation will not go through. Same way, set default will try to set the default value if some default value is provided while creating the table. These are pretty much all the referential integrity constraints that we use on a day-to-day basis to protect our data from going corrupt, to protect our data from going inaccurate, right? So this basically means we cannot delete a user as long as they have some associated projects in the projects table because of this statement on delete restrict, and owner ID is a foreign key. And similarly, we have created it and updated it. Moving on, we have tasks, which another table. And in the same way, we have a primary key called ID, and we have a foreign key here called project ID. It is of type UUID because the primary key of projects is ID, and ID is of type UUID. And since we'll be storing the values of ID here, this is also UUID. And we are saying not null, which means there cannot exist a task without an associated project ID. That cannot be an orphan task. That's what we are saying here. It cannot be null. Then we have the foreign key constraint, the referential integrity thing. We are saying it references projects, and since we have omitted the field, it will check which is the primary key in projects table. Since the ID is the primary key, ID is the foreign key here. Then we have the referential integrity constraint. We are saying on delete cascade. Now, as I've already mentioned, on delete cascade means if we have a project with ID 1, and if we have a task with ID 2 and project ID 1. This is a projects row, this is a task row. And if we delete the projects row with ID 1, it will check that project 1 has associated tasks in the task table. So what it will do is, since we are written on delete cascade, it will delete all the tasks which are associated with the project ID 1 because of referential integrity, which is a very useful concept in relational databases. Then moving on, we have the title field is of type text and not null, and description, which can be null and of type text. Then we have the priority, which is an integer. We can only store 1, 2, 3, 4, etc., etc., and it cannot be null. By default, if the application does not pass any values, we are setting the value 1. Then in the end, we have a constraint of check. In Postgres or any relational systems, we have different constraints. One we have already seen is unique. So for that field, in the whole table, you can have only one value for a particular field, and that value will be unique across the whole table. Then we have not null, which enforces the condition that you cannot set null in this field. Similarly, we have another constraint. These are called constraints or conditions that we are putting on a particular field. Similarly, we have check constraint, which basically using which we can put a particular condition on a field, a custom condition, and the operation, the transaction will only go through as long as this condition is true. Okay, that's what check means. So if we see here, you're saying when we are trying to insert the priority field, if we do not pass anything, set the default as 1. But if we do pass anything, we are checking that the value should be either 1 to 5. That is the condition that we are putting here. The value of priority should be 1 to 5, so that no one can insert some random value like 55 into the priority field. We're only considering from value 1 to 5. Moving on, we have a field called status, and is a custom enum type, which we created at the start, is of task status, and it can have pending, in progress, completed, cancelled. So the status will have our custom type task status. It cannot be null, and by default, the application, if it does not pass anything, we are setting the value of pending here. Then we have a due date, which is of type date. We are not considering time here or time zone. We're just considering date here. Then we have assign to. We again have a foreign key condition. So assign to is a foreign key which references user's ID from the users table. And the constraint, the referential integrity constraint that we are putting here is, if the user of that ID is deleted, and that user's ID is present in the assigned to field in the task table, then for that row, we are setting the value of assigned to as null. That's what this means. And similarly, we have created it and updated it. The nice thing about the foreign key constraint is because you have written that assigned to, or in this case, owner ID, right? Since these are foreign keys, and by default, relational databases have this constraint called foreign key constraint. Because of that, you cannot enter anything into the assigned to field. If you try to enter some random string or some random UUID, it can be a valid UUID, but that UUID has to be present in the users table as a valid ID. If that is not present, then your insertion will fail. Okay, that's what we mean by foreign key constraint. If you write references users, this makes sure that this UUID, whatever UUID that you are passing for this field, this has a corresponding user entry in the users field. Another thing to notice here is this pattern is called one to many, because we are writing project ID here, which is a foreign key, which references the ID field in the projects table, which basically means that if we have a project with ID 1, that can have multiple tasks, right? Multiple tasks in the task table, which refers to this project using the field project ID in the task table, right? It will be one here, and same way it will be one here, it will be one here, it will be one here, right? One project can have multiple tasks in the task table. That's why it's called one to many relationship. And this is how we implement it. The first kind of relationship, which is one-to-one relationship, the way we implement that is we take the primary key of the main table and we create another table, and we make the primary key of the main table as the primary key of the second table also. But instead of writing just ID, we write the name of the table with ID. So because we had the table called users, for a one-to-one relationship with the user profiles table, what we did, we wrote ID and we used the user's primary key from this table as the primary key in this table. And instead of just writing ID, we wrote it as user ID is the primary key in this table. This is how we implemented one-to-one relationship. And the way we implement one-to-many relationship is we take the ID field and we create another table, but we don't make that as a primary key. We keep that as a foreign key only, and we refer to that using the ID primary key, right? That's how we implement one-to-many relationship. In the next one, we'll see how we implement many-to-many relationship. So moving on, this is the last table, which is called project members. The reason we are creating this table is we want to keep track of what are all the projects that a user is part of. At the same time, we also want to keep track of what are all the users that are associated with a project. So you can look at it both ways. And when you have a condition like that, when you take the same thing and you can look at it both ways and it makes sense, that's how we know that it is a many-to-many relationship. Because if we have a user, that user can be part of multiple projects at the same time, right? You can be part of multiple projects at the same time. Same way, if we have a project, that project can have multiple users at the same time, right? A project cannot be limited to a single user. Same way, user cannot be limited to a single project. That's why projects and users have many-to-many relationship. And we want to keep track of that relationship by creating a different table. And usually we call this table as linking table. And we implement this pattern when we are implementing many-to-many relationship, okay, by creating a different table for the sake of maintaining the relationship between two tables. That's why it's called a linking table. And this is how we do it. Okay, we have to make some changes to that. Instead of creating an ID here, what we'll do, we'll remove this. We'll remove this row. We'll take foreign keys from both the tables. So what we'll do is we have project ID here and we have user ID here. Project ID is a reference to the ID field in the projects table, and we are saying on delete cascade. That's the referential integrity constraint. Same way, user ID is a foreign key which references the users table, and the referential integrity constraint is the same thing on delete cascade, which basically means if the project is deleted, delete all the entries in the project members table. Same way, if the user is deleted, delete all the entries in the project's members table. Okay. And in the end, what we'll do, instead of writing unique, we'll write primary key. And what this means is, this is a composite primary key in the technical terms. So it is a combination of two fields which are foreign keys referencing primary keys of two other tables, and we take those two and we create the primary key. So if a user is part of a project, then that will have one entry in project's members table. Let's say you have users table and you have projects table. Okay. And you have users 1, 2, 3 and projects 1, 2, 3. And we want to maintain a relationship that, let's say through some user journey, user 1 was added to project 2. And we want to maintain this relationship in our projects members table. What we can do, we take project ID, since it's a many-to-many relationship. What we do, we take the project ID, which is 2. Okay, this is the project ID, and we take the user ID, which is 1, right? Take the user ID is 1, and this combined will have one entry in the project members relationship, because user 1 being part of project 2 is a single event, right? That cannot be duplicated. User 1 cannot be part of project 2 multiple times. Same way, project 2 cannot have user 1 multiple times. Okay, that's the reason what we did. We took this combination, project 2 and user 1. We took this, we said that these two combined will be the primary key for this table, because primary key implicitly enforces some constraints like unique and not null. So what we are saying, this combination can only have one entry in this table, which will be a unique entry, and that cannot be null. And because it is a primary key, using this combination, we can uniquely identify this row in this table. Hey, this is the crux of how we implement many-to-many relationship in Postgres or any relational database, using a linking table, which will have a composite primary key of the two tables that we are trying to link. The rest of the things remain same. We have created it and updated it, and we have a role field, which is again a custom enum. So we are saying it is a member role, which we have created. If we go to the top, we are saying member role. It can be either owner, admin, or member. Okay. So if a user is part of a project, in that project, whatever characteristics that user will have, or whatever project characteristics for that user it will have, all those informations we can store in the project members table. And because role is specific to the situation where a user is part of a project, that's why we have kept the information of role in this table. Okay, and by default we are setting the role member, and that's pretty much all our up migrations. Same way as I mentioned, we have to mention our down migrations. All the changes that we did, we created a couple of types, we created a couple of tables. Now in the down migrations, what you have to do, we have to revert that, so that when we want to roll down to a particular version, using these statements, our database can do the rollback. Okay, we have to explicitly say that these are the down migrations that the database tool, the migration tool, can use to roll back to a previous version. Okay, and we are simply dropping all the tables, and after dropping all the tables, we are dropping all the types in the reverse order that we created them. That's pretty much all the tables. Okay, so let's go ahead and apply these migrations to our database so that we can see if it works or not. And to apply it, dbmat has a command. You can write dbmat and you can write up. Okay, and it is applying this migration file, and it says applied in this milliseconds. And when we go here, if we do a refresh, and you can see, we expand it a little bit, these are all the tables that we just created. You can go here and you can check the schema. It has project ID, user ID, role. Same way projects have all the schemas, right? Since we have not inserted any databases yet, all these entries are empty. All these tables are empty. And you can also see there is a special table called schema migrations. And this one is created by dbmate. As I've already mentioned, all these migration tools, they have to keep track of what is the current state of the database so that they can decide what migrations to apply, right? So after this, after our first migration, if you create a different file, the database tool will check what is the current version and it will start applying the migrations from that point on instead of duplicating the migrations. And because if it tries to execute the same statements again, it will get an error from Postgres that this table already exists. You cannot run the same statements again. That's the reason the migration tool maintains a table called schema migration. And in that, it has a single field called version, and it keeps track of what is the current version of the migration that we have. Now that we have our tables ready, we want to insert some data into it. Now in production environments, when you actually deploy this backend, you will have normal user flows, right? People will come to your platform, they'll use the front end to sign up with forms, and they'll create projects with different forms. You have these predefined flows when the data will come into your database. But when you're creating your backend, when you're modeling your data for a backend engineer, when you want to test all those changes, when you want to see how the user interactions will look like, basically for testing purposes in development environments, you want to put some test data into your database so that you have something to test with before you deploy whatever changes that you made in the database. For that purpose, we have a concept called as seeding. And seeding basically means you write some script. Usually you create another migration, or you can put it in the same migration also, but the best practices says you create different migration file for seeding data, seeding test data into your database. And it's called seeding. Basically, seeding means putting some test data into your database for testing purposes in development environments. So let's create another migration file with the command dbmate new seed data, and when you press enter, it creates another file called the timestamp and the seed data. Because this timestamp is greater than the previous one, these will be sequentially arranged. And now this is empty. What I'll do is I'll again paste some SQL statements to save some time. Then we can go through what's happening there, how we are inserting the data for seeding purposes. Now, these are all the SQL queries using which we are putting some test data into our database, into our tables. So there is nothing special here. Basic SQL queries. If you've already explored the basics of SQL, the basics of Postgres, well, you understand it. If you're not, then please do it. It'll make understanding this video much easier. So what you're doing, we are using a CT, also called as common table expression, to make it more readable. So we are creating an intermediate table called inserted users, and in that we are inserting some test data into the users table. We are taking some sample emails, some names, some password hashes, and we are inserting it, and we are returning two fields for this SQL query execution, the IDs and the emails of the inserted users. And we are taking that, and this is an intermediate table called inserted profiles. What we are doing here is we're taking the inserted users table, and using this from inserted users, we are doing select the ID of the user, and we are putting the image. Since the avatar URL you have mentioned here, we are putting some static image URL. And for the bio, we are doing a case when. So if email is something like this, then put this bio. If email is something like this, then put this bio. For this, put this bio. Otherwise, put some logic to put different bios for different users. Then for the phone field, we are just inserting some random phone number. Then moving on, same way, we are inserting some projects and etc. using SQL queries. Yeah? Just normal seeding. So let's go ahead and apply these migrations on our database so that we have some data to test with. For applying the migrations, we can do dbmate up, and you do it. It applies, seeds all the data into a database, and we can go to our tool and we can open any table. So as you can see, projects has some entries. You can click on a row, projects, project members, users. All the tables have some entries, and you can check the entries of the table. For users, we have this ID, this email, this full name, password hash. For the second user, we have these entries. When you go to user profiles, we have this user ID, avatar URL, bio. For the second user, this is the bios. For the third user, this is the bio, etc., etc. Like same way, we also have projects, right? So our seeding is successful, and we have some data so that we can start testing now. Now, let's say we have created the tables, we have done some seeding, and now we want to build some APIs. For the first API that you want to build is, you want to fetch the list of all users and you want to send it to the front end. For that, we can write a simple query and do select from users, and we can execute this and we'll get all the entries, right? All the users that exist in the users table. Now, what we want to do is, for each user, we also want to send the profile information, which is on a different table, right? We have the user profiles table. So for each user, we want to fetch the profile information from the user profiles table, and you want to embed that into the user row, and you want to send it to the front end in a single API call. We don't want the user to make a different call for fetching the profile information. That's why we are embedding the profile information before we send it. So let's write the query for that. Usually when we write SQL queries, always start from section, right? Instead of the select section, so that you know exactly where you are drawing your data from. So we write from users u, and this is called an alias. And assigning an alias, usually a 1-letter or 2-letter alias to a particular table name inside an SQL query, makes it more convenient to refer to that table again and again in that query, right? That's why we use aliases. Now, from users table, we want the information of the user. Next thing what we want is, we want user's profile information, which is in a different table, okay? And it is in the user profiles table. Now, the thing that connects these two tables, as we already know, is the foreign key. So each user profile entry, each row in the user profiles table has a field called user ID, which is a foreign key, which refers to the primary key of the users table. So what we can do, we can use the join operation to join the users table with the user profiles table on a condition, which is the user ID should be the same, okay? And to write that, we can say left join. And the reason we are using left join is because for some reason, if the user profile in the user profiles table, there is not an entry for a particular user, okay? It is possible in our backend system, it is possible that the user has never edited their user profile. That's why we have never created an entry for them in the user profiles table. So in these situations, if we go with inner join, we will get an empty result, because what inner join does, each condition, for a particular condition, there should be an entry for both the tables, okay? Since in this case, we want the user information in any case, right? In any case, it does not matter whether they have the profile information in the user profiles table or not, but we want the user's information anyway. That's the reason we are going with left join, so that even if there isn't an entry in the user profiles table, we'll still get the value of the user's information from the users table. Okay, that's the logic behind going with left join. And most of the times we'll be using inner joins and left joins when we are writing SQL queries. Those are the mostly used joins. We want to join with the user profiles table, and we'll name it alias UP. And the condition for the joining is on. The join condition is u.id. The ID field in the users table should be the same as the user ID field in the user profiles table. This is the condition. Okay, this is the condition on which we are joining both these tables. Now we know where we are drawing our data from. Okay, we have joined two tables. We have a join table, and now what we can do, we can select. In the select phase, we'll see what are the data that we want to fetch. Now that we know where we are drawing our data from, we'll see what data we are drawing from. What we'll do, we want to fetch everything from the user row. So we'll say u dot star, comma, we want to add another field in each row called profile. Okay. So for that field, what we want the corresponding row from the user profiles table, and you want to convert it into a JSON, and we want to embed it into a field in the user row called as profile. Okay. For that, what we can do, we write to JSON B, which basically converts a particular row into a JSON. It is a inbuilt function provided by Postgres, and we can use that to convert it. And we can write take up.star, which means take the corresponding row from the user profiles table, convert it into a JSON, and name it as profile before returning. Okay, we have our query now. Now let's try running it. Okay, and when we run it, let's see what the data looks like. And this is what the data looks like. We have all the fields from the users table. We have ID, email, full name, password hash, created at, updated at, and we have an extra field called profile, which is a JSON, and that has all the information from the user profiles table. Okay. Now using this query in a single API, we can send the users data and the user profile data from a single database call, okay, using joins. Another thing to notice here is whatever data, whenever we run a particular query in any relational data, the data that we get returned is in a random format. They don't follow any particular format. So because of that, whenever we run a select query, whenever we are returning a list of data points into our front end, we have to sort it by default using some column. And usually what we do, we sort it by the created at column, because we want to return the data in the reverse order of when they were created, so that the user can see all the latest users. So for that, what we can write order by u dot created at. We want to take the created at field from the users table, and we want to sort by that, and we want to sort by descending because we want the latest entries. And when you do that and run it, we get all the users in the reverse order of how or when they were created. Yeah. And this is what the query for an API of get all users looks like. So if we have an API, something like this /v1/users, if we have an endpoint, which is a get endpoint, our backend can use a query like this, a database query like this, to return all the data to the user. Of course, there will be other processing that will happen, the serialization, deserialization, depending on what language that you are using. If you're using something like JavaScript or TypeScript or Node.js, then the serialization overhead is not that much. But if you're using something like Go, then it has to deserialize into its own struct. Then that struct will be sent by serializing into a JSON format before it gets sent over the internet to our front end, right? This is what a typical get all users endpoint looks like. Now let's see another endpoint, which is something like /v1/users/ a particular user ID. Okay, so we'll write it as user ID. We'll get it as a dynamic parameter in our API, and we can pass that user ID to our database query as a parameterized query. We'll see what parameterized query means, but if you don't understand this part, please watch the previous video where we have done a deep dive on API designing and what are dynamic parameters, how we design these API endpoints, etc., etc., etc. So let's jump into what this query will look like. Fetching the information, the profile information and the user information of a particular user given a user ID from our dynamic parameter. Okay, before we get into that, let's understand what is a parameterized queries. Parameterized query is basically a safety mechanism provided by databases, which basically means before running a query, you can provide a particular slot. You can provide a particular slot and you tell the database that this is your query, and at this position there is an empty slot. But before I execute this query, I will provide the information in this slot. Now the catch is whatever information I provide here, it will be a string. you cannot parse it. You cannot parse it to render it as a database action call, right? It'll just be a string. So if someone passes something very dangerous, like, so we have a query and inside the slot, if you pass like, let's say delete from users, a query which deletes everything, deletes all the users in the database, that will not be considered as a SQL query. Because the way parameterized query works is whatever you pass in this slot, they are considered as a string. Okay, they are escaped in the technical term, and it is a safety mechanism to avoid situations, avoid vulnerabilities like SQL injection, where if you are constructing your query instead of using parameters, you are constructing by concatenating different strings. You are constructing your SQL query instead of using parameters, then you can be a victim to SQL injection. Okay, so this is a very important concept. You can do your own research to understand how SQL injection works, etc., etc. But to simplify everything, whenever you have a dynamic value, in this case, we want to fetch the information of a single user using the ID of that user. So the ID of the user is the dynamic value here. So what we want to do, we want to keep a particular slot in our query, and we tell the database that when we run this query, we are going to provide the ID of the user. But for now, it is just an empty slot. And when we provide the ID, it should just be considered as a user's ID, just a simple string, nothing else. No more power should be given to this particular string. Okay, that's the use of parameterized query. It makes your query more secure to execute. And most of the times, whatever database driver, whatever library that you're using, whether in Node.js or Go, Rust, Python, whatever it is, your database driver, your ORM, they have capabilities to handle all these slots with parameters and etc., etc. Since we are not getting into code or any specific programming language here, we'll be looking at how parameters work in the SQL editor itself. Fortunately, this Table Plus, the software that we are using to write our queries and to see our results, etc., etc., they are providing an interface to provide parameters to our query. So we can see how it works. But in real world, when you're actually building backends, you will handle parameters using your library, using your driver, whatever driver that you are using. Okay. With that, let's write our query to get the information of a single user. For that, we don't really need to change much. We still want all the information of the user from the users table. We still want all the information of the user from the profiles table using this JSON conversion. The only thing that will change is we want to filter by a user's ID. We want a single user's information now. For that, we want to add a where clause. You can write where user's ID, u.id is equals to a parameter. So this is where we are assigning a slot, an empty slot. We are telling that this is the name of the variable. This is called user ID. And this is the whole query. And we are saying that this is the query and this is an empty slot. And when we run this query, we'll provide you the value of this slot so that you can do your comparison and show us the results. So let's run this. And we are shown this dialog so that we can pass the actual value of the user ID. But as I said, in your actual backend environment, you'll be handling this in code in your particular driver or library. So for this, let's wrap this. We have to wrap it in single quotes, right? All the strings in SQL have to be wrapped in single quote to be interpreted as strings. That's why we are wrapping it in string and we are pasting the UUID of the user. Okay. Is the UID. I have pasted it here, and then let's run this. And when we run this, we get the information of a single user, and you can check this is the user's ID. We are still getting all the information from the users table, and we are still getting all the information from the profile table. But in this case, we are only getting the information of a single user using our parameters with the same query. So this, if you remember, was for the endpoint v1 slash users slash colon user ID. So ideally, while routing, when the front end makes the API call with the appropriate UID value, this will be routed to your particular handler. The handler will pass it to your service. The service will pass it to a repository, and it will pass the user ID, the actual UID. You will take the UID and you pass it in the appropriate parameter using the slot thing that I mentioned. And after you get this result, you'll get the result like this, and this will get serialized and transferred over to the front end in JSON format. Now, going back to the get all users API, the get all users query, what if we want to provide some dynamic filters or some dynamic sorts? Usually in APIs like these, where we fetch an array of entities like get all users, get all projects, get all tasks. In the same API, we also have to support some kind of dynamic sorting or some kind of dynamic filtering, or both at the same time. Now the problem is, without using these queries, without constructing these queries in a proper ORM or using a programming language, constructing the SQL query ourselves, showing that part of the mechanism in a SQL editor is a little difficult. But we can imagine how the query might get constructed in an actual programming language when we are actually writing our backend code. And we can focus on just the SQL query part without focusing too much on how we are going to construct the query. So if you want to go back to the earlier query, which was get all users. So when we remove the where clause and when we run this, we're getting all the list of all the users, just as we had before. Now we want to add some dynamic sorts and some dynamic filters. Now let's see what all fields we have in the users table. We have ID, email, full name, password hash. Let's say we want to add a filter condition and we want to filter by the name. And our condition will be, we will pass a first letter of the name and we want to return all those users who have the first letter, adds that particular letter, whatever the front end is passing. That is going to be our filter condition. And for sort, we want to take the sort order from the user and we want to take this field by which the user wants to sort the result. Okay. And as I said, it's a little difficult showing how the query is going to be constructed, because what happens in an actual backend is, let's say this is our query. This is our query payload and it's a paginated query, right? So user can send these all query parameters. They can send a page query parameter. If they don't send it, by default, we are going to set pages 1. Same way, they are going to send a limit parameter. If they don't send it, we set it as something like 10 or 20, whatever makes sense in your use case. Then we come to the filtering part. So as I said, for the filter, we want to filter by the first letter of the name. So let's say we take a query parameter called letter, and if they don't pass it, then in this case, we don't set any default. If they don't pass it, then we set it as null. Or in an actual backend system, we don't include this in our query itself. Okay. When we are constructing our query dynamically, we check that if the user has passed this query parameter or not. If they have passed, we include it in the where clause. If they have not, then we don't include it at all. Okay, that's how we do it in an actual backend system. Same way, we check the sort conditions. Now, the first thing is we want to check, let's say, sort by. We check if this query parameter is present or not. If this is present, then we consider that as a sorting parameter. Usually, we don't allow the user to pass any field as sort parameters. We give them some options that you can either pass, let's say, full name, or by email, or by created at. Okay, we give them some options, some fields from the table that we allow user to pass, and depending on that, we give them the result. And the last thing that we allow them is sort order. What is the order that you want your results in? Whether it is ascending order or descending order. Now, for these two fields, what we do, we check if the user has passed a sort by parameter, then we consider that for the sorting mechanism. If they have not, by default, we take created at as the default sorting parameter. Same way, we check if they have passed sort order or not. If they have, we consider whether it is ascending or descending. If they have not, by default, we take descending. So if the user has not passed any of this, what do we end up with? We end up with these query parameters. By default, we set the page as 1, limit as 10, sort by created at, and order by descending, right? By default, we anyway give them results as per this, but we also give them the option to customize how they want the results, right? Now with that, let's see how we can construct the query. We have our filter, which we are considering as the first letter of the name. We have our sort, and we allow them to sort by email or full name or created at. And we also want to paginate this, since it is a list of all users. Whenever we are creating list APIs, we should most of the time try to paginate it, unless we have a particular reason. We have a particular user interface where we don't want to paginate, but most of the time we should paginate. Okay, now going back to our query, we have this normal query. Now what we want to do, we want to add some more capabilities to this. So the first thing is we want to add the filter condition. We want to give users the ability to filter by the first letter of the name of the user. So what we can do, we say where u dot full name I like means the SQL operator like, but it is case insensitive. So it does not matter whether it is uppercase or lowercase, it will still try to match the pattern. Okay, I like. And inside this, what we do, we pass a parameterized query, and the parameterized query will be say letter. Okay, then we concatenate with, let's say, the percentage sign. Let's run this query and let's provide the letter J, and let's run this, and we are getting 2 results because these 2 users have the first letter of their name starting with J. That's why we are getting these 2 results. Now let's try to run this with another letter. Let's say X. For this, we don't get any results because we don't have any users who have names starting with X. Same way, if we try to run it with something like A, we get the user Alice Brown, right? So the filter part is working as expected. And for those who are not familiar with the basics of SQL, what this we are doing is we are taking the parameterized query, whatever is coming from the front end, and we are concatenating that with this symbol, this percentage symbol. What this means is take the letter, whatever the first letter is. So if we pass J, this is what happens, J and the percentage symbol. And this goes to the I like pattern matching. So what we are saying, give us all the names which is starting with the letter J, but we don't care whatever comes after that. Okay, that's the reason we are getting all the users who have the first letter with J. Okay, now we have our filter condition implemented. Let's go ahead and implement our sort conditions. So as you can see, we are adding the default sort condition created at descending here. Now what we want to do, we want to make it dynamic. So we want to say order by, this is a parameterized query. We want to say sort by, and as order, we also want to make it a parameter. We're saying sort order. Okay, we have our sort conditions. Let's check this, and we have 3 parameters to fill now. So let's provide it as J, and for the sort by, in the backend, we have to construct this parameter in a way that it matches the existing query. Since we are using aliases in our existing query, we have to provide the sort condition in the same way. What we want to do, we want to sort by the emails of the user. So the parameter we should pass is u.email, right? Because we have to match the alias that is existing in this query. Same way, sort order, we want to say descending. And let's run this, and we are getting 2 results, John Doe and Jane Smith. And this is how it is sorted. John comes first, then comes Jane. So let's try to run this again, but this time make it ascending. Now Jane comes first and John comes second. So our sort conditions are also working as expected. Now the last thing, we also want to paginate this query. Since it is a list of all users, we want to paginate this query. Now in the end, we can write the user is trying to fetch page 1. We have page and limit. For the concept of page, if we want to fetch the first page in the query, we have to add something like offset. And we want to take also a parameter for here. So we write page range, we want page. Now the second thing is we also want to take the limit, and for the limit we also take a limit parameter. And now let's run this. We have two more parameters. For now we want page as 0. Now in the actual backend, the user will pass pages from 1 to whatever the maximum amount, and we are setting also the page number as 1. But since we are talking about the actual database query here, we have to pass the first page as 0, right? The offset starts from 0. That's how we want to differentiate between the actual database query and whatever is set for the experience of the user. So we want to start from the offset 0. And the limit is 1. Since we are only getting 2 results for this query, we want to check if the pagination is working as expected or not. That's why we are setting the limit as 1. And when we run this, we are getting Jane Smith as the first result. And when we try to run this again, but this time we want page, the second page. In the backend concept, it is the page 2. And in the database concept, it is offset 1. And when we run this, we are getting John. Okay. So the pagination concept is also working. And as I mentioned, these things will change a fair amount when you are actually writing the SQL query in your backend, because you have to construct all these queries dynamically using your programming language. But to understand what happens at the database level, this example is pretty much enough. So far, we have seen what the database query looks like. For this API, get all users, and this API, get a single user. Now let's proceed to creating a user, which is post/API/users. Let's see what the query for this will look like. Now, if you're already familiar with SQL basics, this is a simple insert operation. What we want to do is an insert call. Insert into users. We want to insert into users table. And what are the columns that we are passing? We are passing email and full name and the password hash, which we'll create in our backend code. But for the sake of this example, we are just passing the password hash. Second, we want to pass the actual values, and let's use parameterized queries here for email, then for full name, and then for password, and at this camel case, password hash. And in the end, we want to return what all users that were created using this query. For that, we can do returning star. So return all the users, all the rows that were created using this query. So let's try to run this. We have to pass all the parameters and in single quotes, since these are all strings, right? So for email, we can do something like test@gmail.com. And for the full name, we can do test, and for the password, any random string, right? For the sake of this example. And let's run this. And we run it. We are getting a single row as a result because we are doing returning star, and we just created one user. We are getting a single user entry. A new user was created, and we're getting all the information for that user. And when we go to the users table, we can see that a new user with test@gmail.com is created and is in the table. Okay, good. And this is corresponding to the post/API/users API. Since we are creating a user, so we did an insert operation and created a user and returned the response in this API. Now let's get to update a user. Now going back, let's go to our query editor, minimize this. Now, as I mentioned before, in our actual backend code, we will be constructing these SQL queries dynamically depending on what are the parameters that is passed from the user. Okay, so for the update API, what the API usually looks like is it is a patch API, and we are giving the user to update certain properties of their profile. Okay, we are trying to update the user profiles table, and we are giving the user a form, some kind of form in the UI to update their profile. So they can update their bio, they can update their phone number, or they can update their image URL in the field avatar URL. For this, we want to make the payload partial. And by that, I mean they can pass either all the three fields or they can pass a single field. But depending on what are the fields they are passing, we only have to update that field. For all the other fields, we don't touch that. Okay. So in the programming language, depending on what you're using, we check what are the fields that the user has passed, and from a set of allowed fields. So let's say we check if bio is present, then take the latest entry, what the user has passed, the latest value of bio, and update that in the database. Same way we check if the phone number is passed, update it. But avatar URL is not passed, then don't touch it, keep it the same. Okay. So with that understanding, going back to our SQL query editor, what query we can write is, after going through our backend code, we have seen that the user has only passed bio and phone number. So this is what the query is going to look like after getting constructed. Okay, we say update user profiles, then set bio equals to, this is going to be a parameterized query, bio equals to bio, comma, they have also passed phone number, and phone equals to phone. We're going to pass these values in our parameterized queries. And we also have to pass for which user we want to update. Usually we'll take this as a dynamic parameter from the URL. As you can see here, we're taking the ID of the user from the URL. So that's what we will pass in our database, right? And we want to update the information, the profile information of a single user, right? So we have to pass that in our parameterized query. For that, we can write where user ID, which is a field in the user profiles table, equals to a parameter called user ID. And in the end, we are saying whatever row that you have updated, return the latest value of that row. And then let's run this. And for bio, we are saying updated bio. For phone number, we are passing a new phone number, and we run this. And when you check it, you can see the bio is updated and the phone number is also updated for this particular user. And that's how an update user API will look like. Now, I want to show something else. If you notice here, we have a field called updated at, and the purpose of keeping this field in a table is every time a particular row is updated, we also have to update this field corresponding to that row, to the current timestamp, the timestamp when the row was updated. And if we check the field, this is same as the created it. This is the same as when the user was first created. It is not updated since we just updated the value right now. This should have the current timestamp, which it is not. Now, usually there are two ways of achieving this. First is the manual way. Every time you are doing an update operation, you can explicitly set the value of updated column to the current timestamp using your application code. You can pass another parameterized query and you can say updated at equals to updated at. Okay, you can do that, or you can use another feature of databases called triggers. And what triggers do is you can set a particular condition, and when that condition is met, you can perform some action. That's the whole idea of using triggers at database levels. So what we are trying to do here is we will set up a workflow using which what we'll say is every time we are updating a particular row in any table, we want to set the updated at field of that row to the latest timestamp using triggers. Okay, we want to make that change so that we don't have to manually change the updated at field every time we update the information of a particular user. Okay, for that we have to write another migration. That is one change that we want to make. The second thing that you should know about, which is very important concept, is indexes or indices. What is database indexing is, right? This is a very important concept and it affects the performance of your queries a lot. Okay, so we have to understand what is indexing and we have to implement it in our own database using a migration. Now let's understand what indexing is in the first place. So going back to our earlier query. So if we go to the history tab here and let's check what was earlier query. So let's say this one. Okay, and we close this and run this. Right, this one, right? There is a select query for the list of all users. Okay, and if you notice here, we are using some conditions here. Let's try to find out what are conditions that we are using. The first thing that you notice is we are joining with another table, and here we are saying the ID of the users table should be same as the user ID in the user profiles table. This is the join condition here, and it is an equality condition. Okay. Same way, another thing that we are doing here is we are sorting by the email field in the users table, and we are sorting in the order of ascending. This is second thing to notice, and I'll explain why we are drawing attention to this part right now. These are the two things. Now coming back to what are database indexes. Index is basically means by the normal definition. If you're familiar with the index section of a book, so we Google it, let's say book index. This is a typical index section of any book. And what we see here is the writer of the book or whoever the publisher is, they have created an index section where they are saying you can find chapter 1 starting from page 8 and chapter 2 starting from page 29, chapter 3 starting from page 35, etc, etc, right? All the chapters are given here and the corresponding page number where you will find the starting of that chapter. And because of this index section, if someone wants to directly skip to chapter 4, they don't have to open the book and they don't have to go page by page. Let's say the book has around, so it says 82. Let's say the book has around 100 pages. So to find the chapter 4, the user does not have to go through 50 pages one by one in order to reach chapter 4, just to find the location of the chapter 4. They don't have to manually skim through 50 pages just for the sake of finding the location of a certain page, right? They can directly refer to the index. They can see that chapter 4 starts from page 54 and they can directly jump to page 54, right? In the same way, when we are talking about databases, going back to our earlier tables, this is the task table. We have a bunch of tasks and every task has a single ID, right? And we can see all the results in this particular format because it is a software which fetches all the rows from our database and shows us in a sequential manner. But when the database stores our data, it is not in a sequential manner, right? Every entry in a row might be somewhere else. Since in the earlier part of this video, we have discussed that the databases that we are talking about, relational or non-relational, these are disk-based databases, which means the database takes our data and stores it somewhere in the disk, somewhere, right? It can be anywhere in a very efficient format. It follows a lot of algorithms, a lot of complex systems goes behind where to store which data, etc, etc. But on a very high level, on a very simple way of understanding, we can assume that each row is stored somewhere in the disk, right? If we have a query where we want to find out the information of this particular task with this particular ID, which we can pass in a parameterized query, and we want to fetch the information of this particular task. What is the brute force way? Without thinking about indexes, what is the brute force way? The database system has a bunch of tasks and it has stored all the tasks in different locations, right? In a physical hard disk. When it gets a query which says that we want the information of this particular task, what it has to do? It has to go through all the tasks one by one to find out if the ID matches this, if the ID matches this, if the ID matches this, etc, etc. And finally, when it reaches this ID, okay, it has a match, it can see that the ID that we have passed, it accurately matches this particular ID. And then what it does, it returns the information of this particular ID to us. And we have our result. Now what happened is we sent a query. The database did a sequential scan. Okay. It went through all the tasks one by one in different locations of the disk. As I said, the database system has a very complex way of storing the data in database, right? And it went to all those locations and it checked whether the ID matches this item, whether the ID matches this item, etc., etc. And until at the end, it found a match and it returned the information, which, as you can already see, is a very tedious and a very time-taking and a very inefficient solution. Okay. Now, since we only have around 6 entries in this table, it might not seem a lot. It is a lot fast, but imagine if we had 1,000 entries or 1,000,000 entries or 1,000,000,000 entries in the table, then going through all those items one by one and checking from different locations of the disk can take a lot of time and can make the query very inefficient. So for that purpose, what the database offers is a feature called index. What index does, in the same way a book index gives us all the page numbers for a particular chapter. If you want chapter 4, we can directly see that it starts from page 28. Same way, on a very high level, not to go into the technical deep dive of how indexes work, how B tree works, etc., which you can do your own research for. But just for understanding the practical purpose of index, why we use indexes for each ID. So we'll understand how index is actually implemented practically, but for each ID. So we can index a particular field of a particular table. Let's say if we index by ID. So what an index contains is, for each ID, we have the location here. Okay. For each ID, like this. Okay. For each ID from here, for each ID, it has a table. For each ID, it has the corresponding location of the row, right? Where exactly in the disk, in the hard disk, the information of this particular task is stored. So it has another table, a lookup table, where it stores the ID of the task and the location of the task. Same way, the ID of the second task, location of the second task, etc., etc. Now that it has an index like this, when it gets a query which says that we want the information of this particular task, what it does, instead of looking through all the items, all the tasks in the disk from different locations one by one, what it does, it refers to the index. It tries to check whether this exists in the index or not. So as you can see, the index is a direct access. It is not stored in different parts of the disk. It is stored at one place sequentially. So it is very fast to go through all the entries. So it checks whether it matches the first one, the second one, the third one, the fourth one, the fifth one, and it finally finds that this entry. So it is somewhere here. This one matches it. So it directly finds this entry in a very short time, and in the corresponding lookup value, it finds the location where exactly the information for this task is stored in the hard disk, and it gets the location, goes to that location directly, and returns whatever value is stored in that location directly to our user, whoever made the database query in the first place. Now, as you can see, compared to the previous operation, which was a sequential lookup, going through different locations across the hard disk and trying to find out whether the ID that we have passed matches the current ID or not, etc., and finally return the result, as compared to this approach where we have a lookup table where we are storing the ID of each item and the location of that item. Okay, and we are directly giving the result of that to the user. That is the purpose of index. Index is basically a lookup table. You can imagine it as a lookup table which has information for a particular field and the location of the particular row for that field. Now that is the first property of the index. It has a lookup table and it can directly access whatever value that you have passed from this table, and it can find the corresponding location of the entry. It can return you the result. The second property of the index is the order of the index. It can be either ascending, it can be descending. So if you remember in the previous query where we are saying we want to return the list of all users sorted by descending order, right? Now for that query to perform as efficiently as possible, because we have a requirement like that, what we can do, first thing is we want to create an index on created at, right? We want to take the field instead of id, we are taking the index created at, and we want to index that field so that when we execute that query, the database can instantly find all the created at fields and the corresponding row for that created at field, and it can return it. The second thing is, because the sort order is also in the picture, we also have to decide in what order we want to index, either ascending or descending or both of them. Okay, we can create different indices, but it all depends on our requirement. So as you can see, by default we are returning the descending order of created at. So when creating the index, we can say that we want to create an index on the field created at in the descending order, so that when we execute that query which has order by created at and descending, the index can quickly go through all the created at field that is already ordered in descending order, and it can quickly return that result, instead of if it had all the created at field in ascending order, then it will have to go through all of that and you have to rearrange and do a sort and then return, right? So depending on our requirement, we can customize the behavior of the indices. Okay, that's a very high level introduction to indices. So what you have to remember is, every time you are using a where clause or a join condition, and depending on what is the frequency that you are doing that, what is the frequency that you are doing the join condition or the where clause, you can decide to create an index on that condition so that the subsequent queries are faster, because how the database does the lookup. So the two things that we saw, one thing is we have to create trigger so that the updated at field is automatically updated every time we update a particular row of the user. Second is we have to create indexes so that the join conditions and the where clauses and the sorting conditions are faster. Okay, so let's go ahead and create a migration which covers all these. I have gone ahead and created a new migration file using dbmate and pasted all the index create statements and the trigger statement. So let's go through and understand what's happening here. What are we exactly doing here? So in the first section, you can see in the up migrations, we are creating a bunch of indices. The first one, we are creating an index on the email field in the users table, because we have, let's imagine we have an API where we have to find a particular user by the email, or we have a database query where we are joining the users table with the task table depending on the email of the user, right? In the join condition, we have the condition where we are matching the email. Because we have a requirement like that, we decided that we want to index the email field of the users table so that in join conditions and in the where clause, we can quickly find the corresponding user given a particular email using the index. And that was the reasoning behind using email or indexing email from the users table. So this is the syntax looks like, is a generic SQL syntax. Same way, we are creating an index on the created field for the users table in descending order. Because if you remember the select query, the get all users API, where we are by default returning all the users sorted by the created field in descending order. Since we have an API like that and it is pretty frequently called, that's the reason we want to optimize the query execution of that particular database query by creating an index on the created at field in the descending order, so that the database can do a fetch operation very fast as compared to a fetch operation without using indices. Okay, same way, for the task table, we are creating an index on the project ID. So if you remember, going back to our first migration where we created the table, we have the task table and we have project ID here. Okay, and this is a foreign key. So imagine we have an API where we are fetching all the tasks of a particular project, right? And for that API, we have to create a database query where we have to take the projects table and we have to join it. We have to left join it with the task table depending on the ID field of the projects table and the project ID field in the task table. That is going to be our join condition, right? These two has to match. Now, as I said, that whatever field is involved in your join conditions or in your where clause, if you index that field, that operation is going to be much faster. Now, by default, whatever field is the primary key of the table, that is by default automatically indexed by your database, right? You don't have to manually do it. So in the join condition, two fields are involved, the ID field and the project ID field from projects table and the task table. So since ID field is the primary key in the projects table, we don't have to think about this. This is automatically indexed by the database. But in the task table, we have the field project ID, which is a foreign key, and this is involved in the join condition. And since it is involved in the join condition, we want to index it because it is not indexed by default. Since it is a foreign key, it is not the primary key in this table. So that is the reasoning behind indexing. In this migration, we are creating an index on the project ID field on the task table because we have a join condition where we want to fetch all the tasks of a particular project, right? For that, we have to make a left join. In the left join, we have a condition where we are matching by the project ID. And that's the reason we want to make that operation little faster. That's why we are indexing by project ID field in the task table. Same way, in the task table, we have an assign to. Okay, this is also a foreign key. So imagine another API where we want to fetch all the tasks of a particular user. So this assign to is a foreign key which references the users table. So this will have a corresponding entry in the users table with ID of that user, right? So to implement that API, what we have to do, we have to take the users table and we have to join it with the task table on the condition that assign to has to match users.id, right? Since ID is the primary key of the users table, we don't have to think about that. But in this table, assign to is a foreign key, right? So we have to index this field to make the join operation of joining users table with task table a little faster. That's why we are creating an index on the assign to field in the task table. Okay. Next, we are creating an index on the created at field in descending order in the task field because the same reasoning. If we want to return the list of all tasks to show it on our front end, by default, the API returns all the tasks sorted by the created at field in descending order because we want to return all the latest tasks, and we can fetch all the latest tasks by sorting all the tasks in descending order. And to fetch all the tasks in descending order, to make that operation a little faster, we are creating an index on the created at field in the task table in descending order, right? Same way, we are creating an index on the status field because in the get all tasks API, let's say we have a filter condition. In the filter condition, what we are doing, we want to fetch all tasks. So if we go to task status, we are creating a custom event type. And we have 4 types of status: pending, in progress, completed, and cancelled. Now let's imagine in the get all tasks API, we want to fetch all tasks which have the status pending. Okay. We have a requirement like that. And the front end, the user can pass any dynamic status, right? The pending, progress, completed, whatever, right? And we want to quickly fetch all the tasks depending on what is the status of this task. And because the status field was involved in a where clause, what is the condition for creating an index, or what is the thumb rule? If that field is involved in join condition or in a where clause or in a sort condition. Okay, these 3 are your primary guidance on when you should consider creating an index for that field. Okay, since status field is used in a where clause, we can consider creating an index on the status field in the task table. Now, another thing is you should not create an index right away whenever you have a condition that field is used in a where clause or a join condition or a sort by. You have to see and you have to evaluate how frequently that query is being called, or if the performance trade-off is worth it or not. Since to maintain an index, the database at all times has to take that field. Let's say we have the project ID field in the task table, project ID, and in the lookup, we have all the locations of the task, right? We have all these entries. To maintain this index, to have the latest state of all the tasks in that index, what the database has to do, every time you do an insert task or every time you do an update task, this index has to be accurately maintained. And to maintain that, every time you do an insert or update, the database has to do some kind of operation to store the latest state of the task in the index table, right? And which adds some kind of overhead, even though it is not a lot, and it depends what is the size of your database, how many entries you have in your database. Index operations themselves can add some kind of overhead. So as a backend engineer, you have to evaluate these conditions, that whether creating an index is worth it or not, whether the overhead of maintaining an index is worth it or not. And that depends on how frequently your database query is executed and what kind of user experience that you want to provide, etc., etc. You have to consider a lot of parameters, but on a very high level, without thinking about all these micro optimizations, you can take these three parameters, that whether that field is involved in a join condition or a where clause or a sort operation. If it is, and you see that that query is frequently called, then you can go ahead and create an index on that. And if you, in the future, you see that that query is not being frequently called, then you can just go ahead and delete that index, right? Okay, but as a start, you can consider creating it and monitoring your performance, etc., etc. Same way, we are creating an index for project ID in project members. We are creating an index on user ID in project members, etc., etc., right? The same logic, the same kind of reasoning applies everywhere. Okay, that's pretty much all about index. Now coming to the triggers part. As I said, we want to automate the operation of every time we update a particular row in any table. We also want to update the updated field of that row so that we don't have to do it manually from our application code. For that, what we are doing, we are creating a function. In Postgres, we have the ability to create custom functions. And we are creating a function and we are naming it something, and we are saying it returns a trigger, and we are starting a transaction. Okay. And what we are saying is take the row and the updated field of that row and update it to the current timestamp and return the new row, whatever with the new value of the updated field. And now we have a custom function that is ready to use. Okay. Next, what we are doing, we are creating triggers on different tables, right? We are taking all the different tables, users, user profiles, projects, tasks, and we are creating triggers on each table. What you're doing, we are naming the trigger something so that it is easier to drop the trigger later on in our down migrations. Okay. And what you're doing, you're saying every time we are doing some kind of update operations on this table, go to that row, whatever row is updated in that operation, and execute this function. And what this function does, it takes the updated field and sets it to the current timestamp. Okay. And with that setup, what happens every time we do an update operation, this will automatically update the updated field for that row. Okay. Now that's pretty much it. We are creating triggers for all the tables, and in the down migrations, we are deleting all the triggers, we're deleting the function, and we're deleting all the indexes that we created. Then we can go ahead and execute these migrations. For that, we can do dbmate up, and this is applied. Now going back to our table plus, let's do that update operation again, right? So we remove this. This was our earlier update operation, right? And let's execute this. Say updated bio 3, okay? And let's apply it and go to this row. And now when you see the updated at field, you can see that this is the current time when I am recording this video, and this is the current date and time. The timestamp accurately matches. So our trigger accurately worked, right? We did some kind of update operation on this particular row, and this field is automatically updated. And that's the use of triggers. Now with that, we have created database queries for all these APIs. Okay. Now going through each of these APIs and creating a database query is going to take a lot of time, at least a few hours more. And I don't want to make this video longer than what it already is. So you can go ahead and with all the reasoning that I have explained here and all the SQL basics and the Postgres basics that you have already learned, you can go ahead and create the database queries for all these APIs, right? And you can see how the join conditions work, how the indexes are coming into place, how the triggers are working, etc., 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 right? And that's pretty much all you need to know. And of course, that's not all you need to know, but that's pretty much 80% of what you are going to be doing as a backend engineer while you are dealing with databases. Okay, you're going to take APIs and you're going to analyze what all payload is coming from the user, and you have to construct a dynamic query. Depending on that, you have to use parameterized queries to securely pass whatever user value that you have, and you have to execute that query and you have to return the data, right? That's a very high level walkthrough of what you're going to be doing as a backend engineer when it comes to databases. Of course, there are a lot of other things, but this pretty much covers on a very high level the most of the things that you'll be doing.